What if the universe is hiding truths so deep they warp the very fabric of reality? What if there are more dimensions than we can see, stacked all around us like invisible pages in a cosmic book? And deeper still, what if the greatest mystery isn't out there in the stars, but inside your own mind? Why did matter suddenly awaken and begin asking questions? Why do atoms think, feel, and dream? These are the secrets the universe doesn't want to give up. And today, we're unlocking 10 of its greatest cosmic mysteries. Secret number 1. Are there other dimensions? We experience the universe in 3 dimensions of space: length, width, and height, and 1 of time. But some of the most ambitious theories in physics suggest that this is only a fraction of reality. According to string theory, all particles, electrons, quarks, photons, are not point-like, but instead tiny vibrating strings of energy. The catch: these strings can only make sense mathematically if the universe contains more than the 4 dimensions we experience. Most versions of string theory require 10 or 11 dimensions. That means there could be 6 or 7 hidden dimensions, curled up so tightly we don't notice them, like a sheet of paper folded into a tiny cylinder. Physicists call this concept compactification. Just as a tightrope walker only moves forward and backward while an ant can circle the rope in hidden directions, these extra dimensions could be all around us, coiled into microscopic loops too small to detect, but their presence could help unify gravity with the quantum world, resolving the biggest rift in modern physics. But what if these dimensions aren't just small? What if they're large, but we're trapped in our own? That's the idea behind brain cosmology, a model in which our entire universe exists on a kind of 3-dimensional membrane or brain, floating in a higher dimensional space called the bulk. In this view, other universes could exist on parallel branes, just millimeters away, but entirely inaccessible. Some physicists have even suggested that gravity's relative weakness might be explained if it leaks into these extra dimensions. That's why experiments at places like the Large Hadron Collider sometimes search for missing energy, hoping it signals that a particle has slipped into a dimension we can't perceive. And it gets even wilder. In M theory, the 11th dimension might allow entire universes to collide and rebound, triggering new Big Bangs, an endless cosmic dance across higher dimensional space. We don't yet have direct evidence of extra dimensions, but the math works, and the implications are staggering. If they exist, it means our entire universe is just a slice of a much larger reality, like a shadow cast by something far more complex. We may be 4-dimensional creatures trying to map a world far beyond our comprehension. So the next time you look around, consider this. Everything you see might be just the surface of something unimaginably vast, folded just out of reach. Secret number 2. What is dark matter? Take everything you've ever seen, every star, every planet, every galaxy, and understand this. It's only about 5% of what's really out there, the rest mostly invisible. Roughly 27% of the universe is made of something we call dark matter, a mysterious substance that doesn't emit, absorb, or reflect light. We can't see it, we can't touch it, but we know it's there. Why? Because we can feel its gravity. In the 1930s, astronomer Fritz Zwicky noticed that galaxies within clusters were moving far too fast. So fast that they should have torn themselves apart. Something unseen, something massive, had to be holding them together. Later, astronomer Vera Rubin measured how stars orbit within galaxies. Strangely, stars on the edges were moving just as fast as those near the center. The only explanation? A halo of invisible mass surrounding the galaxy, exerting a gravitational pull. And so the hunt for dark matter began. But what is it? The leading theory is that dark matter is made of unknown particles, perhaps WIMPs or axions or even sterile neutrinos. These particles wouldn't interact with ordinary matter except through gravity and perhaps the weak nuclear force, making them incredibly hard to detect. Dozens of experiments buried deep underground are listening for the faintest collision between dark matter and regular atoms, but so far, nothing. Another possibility? That gravity itself works differently on cosmic scales. Modified gravity theories like MOND or emergent gravity try to explain galactic motion without dark matter, but they struggle to match the data across all scales. We also see the influence of dark matter in the cosmic microwave background, in gravitational lensing, where light bends around invisible mass, and in galaxy formation simulations. Without it, the universe would look radically different. Galaxies wouldn't have clumped together the way they have. There would be no cosmic web, no us. And yet, despite all this, we've never directly seen a dark matter particle. It's the ghost in the machine, everywhere and nowhere, holding galaxies together, shaping the universe's skeleton, yet eluding even our most sensitive detectors. So we keep looking. Because if we find it, we won't just be explaining an invisible ingredient, we'll be rewriting the fundamental recipe of reality. Secret number 3. What is dark energy doing, and will it stop? In 1998, astronomers staring deep into space found something no one expected. The universe is expanding faster and faster. This discovery shattered our assumptions. For decades, we thought gravity would slow the expansion of the cosmos, but instead, some mysterious force was pushing everything apart. We named it dark energy, a placeholder for something we don't yet understand. Today, we believe dark energy makes up a staggering 68% of the entire universe. But what is it? One theory is that dark energy is the cosmological constant, a fixed energy embedded in space itself. As the universe expands, more space means more dark energy, which leads to more expansion, a self-reinforcing cycle. This idea fits well with general relativity and explains what we see, but it doesn't tell us why this energy exists or why its strength is what it is. Other theories suggest dark energy isn't constant at all. Maybe it's a dynamic field, like a form of evolving energy that changes over time. Some call it quintessence, a hypothetical energy field that fills space, but ebbs and flows. If that's true, then the fate of the universe depends on what this energy does next, and that opens the door to terrifying possibilities. If dark energy becomes stronger over time, it could tear galaxies apart, then stars, then atoms. This scenario is called the Big Rip, a future where space expands so violently that even subatomic particles are torn asunder. But what if dark energy fades away entirely? The universe might slow down, coast, or even reverse its expansion into a catastrophic big crunch. And here's the twist, we have no idea which, if any, of these fates will come to pass. Our current observations only give us a snapshot. We don't know if dark energy is static or changing because we've only observed a small piece of cosmic time. So we live in a universe driven by an unseen force, one that's expanding space, rewriting physics, and determining our ultimate fate. We call it dark energy. But what it really is, still one of the universe's best kept secrets. Secret number 4. Are we alone in the universe? There are more stars in the universe than grains of sand on all the beaches of Earth. Around those stars orbit billions, perhaps trillions, of planets. And yet, we've heard nothing. No signals, no spacecraft, no unmistakable signs of life. This eerie silence is called the Fermi paradox, named after physicist Enrico Fermi, who famously asked, "Where is everybody?" Logically, the cosmos should be teeming with intelligent life. If even a tiny fraction of civilizations developed advanced technology, they could colonize their galaxies in a few million years, a blink on the cosmic clock. So why haven't we seen any sign of them? Secret number 5. Why does time only flow forward? You wake up, you grow older, you remember yesterday, but not tomorrow. Why? This might seem obvious. Time moves forward, right? But here's the thing. The fundamental laws of physics don't care whether you're looking at Newton's laws, Maxwell's equations, or even quantum mechanics. They work the same whether time is moving forward or backward. So why don't we ever see scrambled eggs leap back into whole eggshells? The answer may lie in one haunting concept: entropy. According to the second law of thermodynamics, in any closed system, entropy, the measure of disorder, tends to increase. Imagine a deck of cards perfectly ordered by suit and number. Shuffle it and it becomes chaotic. Technically it could return to perfect order by random chance, but the odds are so astronomically low, it's effectively impossible. In the same way, the universe began in a state of unimaginably low entropy, a pristine, orderly singularity, and has been drifting toward higher entropy ever since. This arrow of time is tied not to the flow of time itself, but to the flow of entropy. We experience time in one direction because we're passengers on entropy's one-way street. But there's more. The arrow of time affects our memory. We remember the past because information from it is encoded in the present. Neural patterns, carbon isotopes, fossils. There are no records of the future because it hasn't happened yet, or perhaps because it's not recorded anywhere. Some physicists suggest that time might not flow at all. In theories like the block universe, past, present, and future all exist simultaneously. Time is like a frozen landscape, and our consciousness simply moves through it, giving us the illusion of flow. Others propose that time emerges from deeper quantum processes, perhaps linked to entanglement or information. And then there's the mystery of cosmic time symmetry. If the universe's entropy increases toward the future, why was the beginning so special? Why did it start with such low entropy at all? No one knows. Time, our constant companion, our most precious resource, is still a mystery, and understanding it may require unlocking secrets deeper than gravity, deeper than quantum mechanics, perhaps even deeper than reality itself. Secret number 6. What came before the Big Bang? It's one of the most haunting questions in all of science and philosophy. What happened before time began? According to the standard model of cosmology, space and time themselves emerged from a singular event about 13.8 billion years ago, the Big Bang. But that leaves us with a mind-bending riddle. If time started at the Big Bang, can there even be a before? The short answer, we don't know, but the long answer, it's fascinating. Some theories suggest the Big Bang wasn't the beginning of everything, but rather a transition from one state of reality to another. In loop quantum cosmology, for instance, the universe doesn't spring from a singularity, but bounces from a previous collapsing cosmos. In this view, the Big Bang is more like a big bounce, a kind of cosmic heartbeat, where expansion follows contraction in an eternal cycle. Then there's eternal inflation, a theory proposing that our universe is just one bubble in a frothing cosmic foam. In this scenario, before the Big Bang might lie in a larger multiverse where new universes constantly bud off from inflating space. Each Big Bang births a different cosmos with its own laws of physics. Ours just happens to be one of them. Still others turn to string theory or M theory, where space and time are emergent properties, not fundamental. In these models, the Big Bang could be the result of a collision between higher dimensional brains in a larger unseen reality. What we perceive as a single point of origin may be the aftershock of something bigger happening in dimensions we cannot perceive. But there's another possibility that challenges the very question. Maybe asking what came before the Big Bang is like asking what's north of the North Pole. If time itself began with the Big Bang, then before might be a meaningless concept, our language breaking down in the face of something deeper than space, time, or cause and effect. Some physicists, like Stephen Hawking, embraced this idea. He proposed that at the origin of the universe, time becomes imaginary, in a mathematical sense, smoothing out the singularity and removing the notion of a sharp beginning. The universe, he suggested, may be finite but unbounded, like the surface of a sphere which has no edge and yet is not infinite. So what came before the Big Bang may be another universe, maybe a different kind of time, maybe nothing at all. But one thing is clear: if we ever unlock this mystery, we may uncover not just our cosmic origin, but the blueprint of all existence itself. Secret number 7. What are black holes really like inside? To call black holes mysterious is like calling fire warm. These cosmic monsters are among the strangest, most extreme objects in the universe. So powerful, they warp the very fabric of space and time. But what lies inside them? That's where things get weird. From the outside, a black hole is defined by its event horizon, a one-way boundary beyond which nothing, not even light, can escape. But what happens after you cross that threshold? General relativity predicts a singularity, an infinitely dense point where space-time curves infinitely and our known laws of physics collapse. But infinities are often a sign that our theories are incomplete. Some physicists believe the singularity is not a real place, but a symptom of using the wrong tools, like trying to describe quantum processes using only classical physics. This has led to speculative but exciting alternatives. One such possibility is the gravastar, a hypothetical object where, instead of collapsing to a singularity, matter condenses into an exotic quantum state that halts the collapse just shy of the event horizon. To an outside observer, it behaves much like a black hole, but inside it may be something entirely different. Then there's the firewall paradox. Some theories suggest that anyone falling into a black hole would be incinerated at the event horizon by a wall of quantum energy. But this contradicts Einstein's general relativity, which says you should feel nothing special as you cross it, no drama, as physicists like to say. Resolving this paradox has led to radical ideas about the nature of reality, including holographic duality, information scrambling, and even the possibility that space and time themselves emerge from quantum entanglement. Which brings us to the black hole information paradox. What happens to information that falls into a black hole? Quantum mechanics says information can't be destroyed, but black holes seem to erase it. Hawking radiation, an effect predicted by Stephen Hawking, allows black holes to slowly evaporate over time. But what happens to the stuff they swallowed? Some believe that information is encoded in the radiation itself, just in an unimaginably scrambled way. Others think it gets trapped on the event horizon in a holographic form. And still others propose that black holes could be gateways, bridges to other parts of the universe, or even to other universes entirely. And yes, this is where wormholes come in. If certain conditions are met, a black hole could connect to a white hole, a theoretical object that expels matter instead of sucking it in. Together, they could form a traversable tunnel through space-time, a wormhole. These exotic structures appear in solutions to Einstein's equations, but require exotic matter with negative energy to stay open. Whether such matter exists remains unknown. So what are black holes really like inside? Are they singularities, quantum stars, holographic prisons, portals? We don't know, and we can't look directly inside to find out. But if we ever solve this mystery, we won't just understand black holes. We'll understand space, time, information, maybe even reality itself. Secret number 8. What sparked consciousness in the universe? The universe began as energy and matter, so how did it come to know itself? Somewhere along the line, lifeless atoms assembled into something that could see, feel, wonder, and ask questions like this one. The mystery is consciousness, and we still don't know how or why it arose. From a biological perspective, consciousness is often described as an emergent property of the brain, a kind of computational awareness arising from the complex firing of neurons. But that only pushes the mystery further back. How does a network of cells generate subjective experience? Why does anything feel like something from the inside? This is the hard problem of consciousness, famously described by philosopher David Chalmers. We can understand the mechanics of perception, memory, and behavior, but explaining qualia, the raw feel of an experience like the redness of red or the pain of loss, is something else entirely. Secret number 9. How will the universe end? The universe had a beginning, so how does it end? For centuries, this was the domain of philosophy and religion. But today, physics offers several dramatic scenarios, each one grounded in real data, and each one more haunting than the last. The most widely accepted theory is the heat death, also known as the Big Freeze. In this vision, the universe continues expanding forever, but more and more slowly. Galaxies drift apart, stars burn out, and black holes evaporate. Eventually, only a thin, cold fog of particles remains, spread so thin that nothing more can happen. No heat flow, no chemistry, no thought, just stillness. Entropy wins. This is the quietest apocalypse imaginable, not a bang, but an eternal whimper. But not all endings are so gentle. There's the big rip, where dark energy, the mysterious force causing cosmic expansion, doesn't stay constant. It accelerates. If it grows stronger over time, its repulsive force could eventually overwhelm all other forces, even gravity and the bonds between atoms. Galaxies would tear apart, then solar systems, then planets, then molecules. In the final moment, space itself would be pulled apart, a singularity of expansion, or perhaps the universe collapses instead. The Big Crunch is the opposite of the Big Bang. If the density of matter or the behavior of dark energy changes in just the right way, gravity could one day reverse the expansion. Galaxies would fall inward, the night sky would brighten with onrushing stars, and everything would collapse into a final singularity. It might be the end, or a reset, which brings us to the Big Bounce, a cycle of universes. In this theory, the end of one cosmos triggers the birth of another. After each crunch, a new bang. Time becomes a wheel, not a line. Could this be the millionth universe to rise and fall? And then there's vacuum decay, arguably the most terrifying. According to quantum field theory, the vacuum of space might not be truly stable. It could be a false vacuum, a fragile state that might one day snap into a lower energy state. If that happens, a bubble of true vacuum could form and expand at near the speed of light. Everything it touches is annihilated instantly. Not even the laws of physics survive. And we'd never see it coming. More exotic possibilities include quantum collapse, multiverse transitions, or endings we haven't imagined yet, shaped by forces we don't even understand. The universe may freeze, fall, burn, bounce, or vanish in an instant. Each scenario has its own timeline. Some take trillions of years, others could happen tomorrow, and all of them remind us of something profound. This moment, right now, is a miracle of structure and warmth, a fleeting breath in an eternal night. Secret number 10. What is the universe, actually? We live inside it, we measure it, we explore it, but ask the simplest question: what is the universe, really? And you enter the deepest rabbit hole of all. Is it just matter and energy expanding through space? Or is space itself a thing, woven from some invisible fabric? Quantum physics tells us that particles aren't really particles. They're waves of probability, clouds of maybe. Everything solid is, at its core, empty space, governed by uncertain rules. At the smallest scales, the universe stops behaving like a machine and starts behaving like an idea. General relativity, on the other hand, treats the universe like a fluid tapestry, space and time, bending and flowing under the weight of energy. According to this view, gravity isn't a force, it's geometry, and black holes may not just bend space, but tear holes in its foundation. Some physicists believe the entire cosmos is a hologram, a projection of information encoded on a distant boundary, much like a three-dimensional image on a flat credit card. In this view, everything we experience might be an emergent illusion, rising from bits of quantum information playing out beyond our perception. Then there's the simulation hypothesis, that our universe may be a vast digital program running on a substrate we'll never access. If true, space and time might be computational, consciousness could be code, and the Big Bang, the boot-up moment, or maybe the universe is a quantum wave function, a boundless superposition of all possible realities, unfolding according to probabilities and collapsing only when observed. Which begs the question, who or what is the observer? In the end, all our models are metaphors, useful, predictive, testable, but still incomplete. Our brains evolved to hunt, build, and love, not to intuit extra dimensions, entangled particles, or the nature of space-time itself. But that hasn't stopped us from trying. The universe might be a thing, a thought, a simulation, or something else entirely. And yet, here we are, thinking about it, wondering what it means, asking questions the cosmos seems determined not to answer. But maybe the search is the answer. Maybe the meaning of the universe is that we're here to ask what it is. We've journeyed through black holes and multiverses, pondered consciousness and the birth of time, stared into the darkness between galaxies, asking questions the universe refuses to answer, and yet we ask them anyway, because that's what it means to be human, to wonder, to reach, to imagine what lies beyond the veil. Maybe we'll never know what dark matter really is. Maybe the final fate of the universe will forever remain a mystery. Maybe the truth is stranger than anything we can conceive. But in asking, in searching, we become more than just matter, we become meaning. The universe may keep its secrets, but the fact that we seek them, that we can, is a miracle all its own. Thanks for watching the secrets the universe doesn't want to give up. If you enjoyed this video, please subscribe to Stellar Stories for more journeys into the unknown. This channel is tiny, and every interaction from you helps me immensely. And I'll respond to all your comments. The cosmos is vast, but curiosity connects us all. See you next time.